Hello, everyone. I'm Zach.
And I'm Madison.
Eric couldn't make it with us tonight, but we are the Beam team. In this video, we'll be analyzing the Hilltop Apartments Community Center structure.
Our building is a single-story building with an attic space made of a steel frame structure with brick exterior walls, a wooden asphalt shingle roof, and it contains an office space, kitchen, and a lounge.
The focus of this project is we will be analyzing this central beam, as you can see in the picture to the right. The loading reactions are on the central beam. Each end is fixed, and there are 3 columns in the center. We will determine the static building loads based on the ASC 7. We will calculate the support reactions under extreme wind conditions of 150 miles an hour, and we will get the necessary information from design codes from ASC 7.
The dimensions of our building were attained through the building's floor plan. The span length couldn't be determined with, or it could be determined with a tape measure. It was harder to visualize through the
Keep going. Blueprints.
blueprints, and no beam sizing was available or visible from the inside. So we used assumptions from previously constructed buildings in order to determine that. And this is the dimensions created through SolidWorks.
To calculate the beam size of the interior beam, once again, the codes were taken from ASC 7 standards. We found that the roof load for the dead load of a 4.2 or a 412 pitch roof was about 15 pounds per square foot, and the live load for the regional snowfall was 35 pounds per square foot. So added together, that had a total roof load of 50 pounds per square foot. For the attic itself, the dead loads were 20 pounds per square foot, and the live were 20, making a total of 80.
This is the total roof and attic loads on the girder themselves. And this just shows the dimensions and the free body diagram of the building.
To find the beam sizing of the column we will be analyzing, Eric found the allowable stress and the minimum section modulus based on the equation shown on the screen. And these were used to determine that the beam is a W10 by 12, and all of the standards match with the ASC 7 standards for the building codes. And this is where there's a check for the beam deflection and compressive strength. So the maximum deflection, as you can see, is 0.375 inches, and the maximum deflection for design loading is less than the maximal allowable, so it meets the standards. And the max compressive strength is 12.5 kPa per square inch, and that is less than the 18 kPa per square inch. So the W10 by 12 wide flange steel beam meets the design specifications.
This is the free body diagram of the top of the beam. It shows the assumption we made that the columns were each represented as pins and the ends of the beam are being considered fixed, with the girder load being shown as the 6,400 pound point loads. These are the beam reactions calculated using the slope deflection method for that beam.
And this image here shows the slope deflection calculations. Once again, the assumptions were that each end was fixed and the interior columns were pins. And we use the deflection equations and combine them to make sure, or to get the necessary loading for the deflection.
And in the next few slides, we'll show the structure under extreme wind loading.
This image here shows how the frame is put under load for the 150 mile an hour winds. This loading was taken from the ASC 7. I think the maximum load, or the design load, is about 110 miles per hour. So we decided to bump it up to 150 for an extreme condition. And as you can see, the 14.5 kip and 7 kip loads were put on the frame, and this is how they will be analyzed.
This pictures the wind loadings on the structure using the portal method in order to find all of the shearing in the X and Y direction as well as the moment underneath of each of the columns.
And then this table here sums everything up into one nice table. As you can see, each point has a force in the X, Y, and Y direction as well as a moment. And this is analysis of the same beam in STAD Pro. I drew up the beam with the necessary supports and loading and found the location of the max vertical displacement in each beam section as well as the displacement. And this shows the maximum wind loading. As you can see, there's the distributed load from the weight of the roof and the girders above, and the wind load is coming in the X direction on the side. And this table sums up all the wind loads, or the displacements due to the wind load and distributed loads from the previous picture into one table for comparison.
And that's all we've got. Thanks for listening.